November 7, 1943, North American Aviation Factory, Inglewood, California. In the transmission testing facility where every component destined for the P-51 Mustang underwent precision verification, Senior Inspector Margaret Hastings discovered an anomaly that should have triggered immediate rejection. The reduction gear assembly before her, a critical component linking the Packard V1650 Merlin engine to the propeller shaft, exhibited angular misalignment measuring 0.04 of an inch off specification. By every standard in the quality control manual, this was a failure. The tolerance window for gear mesh alignment was plus or minus 0.02. The component before her exceeded that specification by 100%. Hastings prepared to mark the unit for rejection and returned to manufacturing when something made her pause. The test data showed anomalous vibration damping characteristics at high rotational speeds. The misaligned gear was producing harmonic frequencies different from specification units, not worse, just different. Against protocol, she authorized additional testing before rejection. What emerged from those tests would challenge fundamental assumptions about precision manufacturing, reveal unexpected physics in rotating assemblies operating at extreme speeds, and ultimately save the Mustang from structural failures that were killing pilots at the edge of the aircraft's performance envelope. The gear that was wrong by measurement was about to prove essential by physics. The North American P-51 Mustang entered operational service in late 1943 as the answer to a critical strategic problem: how to escort American heavy bombers deep into German territory and return. Powered by the Packard-built Rolls-Royce Merlin engine generating 1,490 horsepower, the Mustang combined speed, range, and maneuverability in proportions that no previous American fighter had achieved. At 25,000 feet, the aircraft could exceed 440 miles per hour in level flight. In combat dives, pilots reported speeds approaching and sometimes exceeding 500 miles per hour, velocities that pushed the airframe into aerodynamic regimes where compressibility effects began influencing control authority and structural loading. The Mustang's performance came with aerodynamic challenges that engineers were only beginning to understand. At high subsonic speeds, airflow over the wing began experiencing local shockwave formation. These shockwaves created buffeting that transmitted through the airframe as intense vibration. The propeller reduction gear, a complex assembly of precision-cut gears that reduced engine crankshaft rotation from 3,000 RPM to propeller speeds around 1,200 RPM, sat directly in the load path where engine torque, propeller thrust loads, and airframe vibration converged. Under normal flight conditions, the reduction gear operated within design parameters established through extensive ground testing, but combat operations were revealing that normal conditions were statistical fiction. Pilots diving from altitude to intercept German fighters routinely exceeded design velocities. The combination of high-speed airflow, propeller thrust at extreme RPM, and airframe buffeting created vibration patterns that were literally shaking reduction gears apart. The failure mode was insidious. Gear teeth would develop microscopic stress cracks under cyclic loading. These cracks propagated slowly, invisible to standard inspection, until catastrophic tooth failure occurred. When a gear tooth shattered at combat power settings, the results were immediate and often fatal. Loss of propeller drive meant loss of thrust. At high altitude over enemy territory, a powerless fighter had limited glide range and even more limited survival prospects. Through October and November 1943, the 8th Air Force reported 9 P-51 losses attributed to reduction gear failure. 3 pilots were killed. 6 were captured after forced landings in occupied Europe. The loss rate was statistically small, but strategically concerning. The Mustang was being deployed in increasing numbers as the primary long-range escort fighter. Gear failures threatened to undermine confidence in the aircraft precisely when operational doctrine was being restructured around its capabilities. The engineering response focused initially on material improvements. Metallurgists at Packard examined failed gear assemblies, analyzing fracture patterns and stress concentrations. The gear teeth were manufactured from SAE 9310 nickel-chromium molybdenum steel, carburized and heat-treated to achieve surface hardness exceeding 60 Rockwell C while maintaining core toughness. The material specification was identical to reduction gears used successfully in other applications. The manufacturing process followed precision grinding protocols that produced tooth profiles accurate to within 0.005 of an inch. By every measurable parameter, The gears were being built correctly, yet they were failing in service at rates that exceeded predictions based on laboratory fatigue testing. The discrepancy suggested that operational loads differed from test conditions in ways that standard engineering analysis had not captured. Dr. Raymond Mueller, a vibration specialist working at Wright Field in Ohio, proposed an alternative hypothesis. The failures were not material defects or manufacturing errors, but rather resonance phenomena emerging from the specific vibration environment inside the Mustang at high speed. Every rotating assembly has natural frequencies at which it will vibrate preferentially when excited by external forces. If the airframe buffeting frequencies coincided with the reduction gear's natural frequencies, resonance amplification could create stress levels far exceeding those predicted by static load analysis. Mueller's theory was elegant but difficult to test. Measuring vibration inside an operating reduction gear at combat power settings and high-altitude flight conditions exceeded available instrumentation capabilities. What was needed was not better measurement but better understanding of how the system actually behaved under operational conditions rather than laboratory conditions. This was where Margaret Hastings's anomalous gear assembly became relevant. The misalignment that should have disqualified the component had altered its vibration characteristics in ways that might, if Mueller's theory was correct, actually improve performance under the specific conditions that were causing failures in specification-compliant gears. The hypothesis was counterintuitive enough that formal testing protocols would never have authorized it. Deliberately introducing misalignment violated every principle of precision manufacturing. But the combat loss rate was high enough that unconventional approaches were becoming acceptable. With authorization from North American's chief engineer, a small batch of intentionally misaligned reduction gears was manufactured. The misalignment was carefully controlled, exactly 0.004 of an inch matching Hastings' original discovery. The units were subjected to vibration testing across a range of frequencies corresponding to high-speed flight conditions. The test results defied conventional engineering wisdom. Under laboratory conditions simulating cruise flight, steady loads, minimal vibration, the misaligned gears performed slightly worse than specification units. Efficiency was marginally reduced. Noise levels were measurably higher. These were the characteristics that justified tight manufacturing tolerances in the first place. But under conditions simulating high-speed flight with airframe buffeting, cyclic loads at frequencies between 80 and 120 Hz, equivalent to the shockwave buffeting measured on Mustangs at speeds above 450 miles per hour, the misaligned gears demonstrated remarkable vibration damping. The deliberate misalignment had shifted the gear assembly's natural frequencies away from the problematic range, where resonance amplification occurred. Instead of magnifying buffeting forces, the misaligned gears were absorbing them through what engineers called detuning. The system was being deliberately made imperfect in a way that prevented destructive resonance. Dr. Mueller's analysis revealed the underlying physics. A perfectly aligned gear mesh operates with minimal internal friction and maximum efficiency, but this efficiency also means minimal energy dissipation. When external vibration excites the system at its natural frequency, there is nothing to prevent resonance buildup. The misaligned gear mesh introduced controlled friction and micro-impacts between gear teeth that dissipated vibrational energy as heat. The system was less efficient but more stable under dynamic loading. The engineering team faced a philosophical dilemma that went to the heart of manufacturing practice. For decades, precision had been understood as the path to quality. Tighter tolerances, more accurate machining, better alignment, these were the principles that had driven manufacturing progress since the Industrial Revolution. Now they were being told that deliberate imprecision, carefully controlled misalignment, produced superior performance under certain operating conditions. It contradicted everything their training had taught them. Yet the test data was unambiguous. Captain Thomas Hayes, a test pilot who had experienced reduction gear failure and survived only through remarkable skill and considerable luck, flew evaluation missions with both standard and misaligned gear assemblies installed. His report was characteristically blunt. The misaligned gear sounds rougher on the ground. You can hear the difference, but at high speed under combat loads, the aircraft feels more solid, less vibration transmitted to the controls, more confidence that the drivetrain will hold together when you push it hard. I don't care what the theory says. The misaligned gear works better where it matters. The decision to implement the misalignment as standard production practice required navigating institutional resistance that ran deeper than mere technical conservatism. The Army Air Force's procurement system was built on the principle that contractors must meet specifications exactly. Deviation from specification, even beneficial deviation, created precedents that threatened the entire quality assurance framework. If North American could deliver deliberately misaligned gears because combat testing showed superior performance, what would prevent other contractors from justifying their manufacturing defects as performance optimizations? Colonel Walter Davidson, responsible for fighter aircraft procurement at Wright Field, articulated the dilemma in a January 1944 memo. We face a choice between theoretical correctness and operational effectiveness. Standard gears meet specification but fail in service. Misaligned gears violate specification but survive operational conditions that destroy standard units. The intellectually comfortable choice is to reject the misaligned gears and demand that the contractor solve the problem within specification. The practical choice is to accept that our specifications were written without full understanding of operational conditions and must be revised based on combat experience. His recommendation was to authorize the misalignment as a specification change rather than a deviation. This preserved the principle that contractors must meet specifications while acknowledging that specifications themselves could be wrong and must evolve based on operational data. The revised specification was issued in February 1944, formally requiring reduction gear assemblies to incorporate angular misalignment of 0.004 of an inch, plus or minus 1/1000th. What had been a manufacturing defect became a manufacturing requirement. The change required retooling across the production chain. Gear cutting tools had to be adjusted. Inspection fixtures needed recalibration. Quality control procedures were revised to reject gears that were too well aligned. The industrial adjustment was completed within 6 weeks, a timeline that reflected wartime manufacturing flexibility and the urgency of preventing further combat losses. The first P-51s equipped with specification misaligned reduction gears entered operational service with the 357th Fighter Group in March 1944. The squadron operated from RAF Leiston in England, flying bomber escort missions deep into Germany. The operational environment was exactly what the engineering solution had been designed to address: high-altitude combat requiring maximum performance, frequent high-speed dives to intercept German fighters, and extended duration missions where mechanical reliability was essential to survival. The combat data from spring 1944 provided definitive validation. The 357th Fighter Group, flying Mustangs with misaligned gears, reported 0 reduction gear failures across 1,147 combat sorties between March and June. Other P-51 units still operating earlier aircraft with standard gears continued experiencing failures at rates consistent with previous months, approximately 1 failure per 200 high-stress sorties. The reliability improvement was not marginal. It was categorical. Aircraft that had been vulnerable to catastrophic mechanical failure at extreme flight conditions were now operating with confidence at the edge of their performance envelope. Pilots who had previously limited their dive speeds out of concern for structural or mechanical failure were now exploiting the Mustang's full aerodynamic capability. Lieutenant Colonel John Meyer, an ace who had finished the war with 24 confirmed victories, described the operational impact. Before the gear change, there was always a voice in the back of your mind saying, "Don't push too hard, don't dive too steep, don't stay at high speed too long." You knew guys who had lost engines in combat and didn't make it home. After the change, you stopped thinking about the gear. You focused on the enemy. The aircraft felt like it would hold together no matter what you asked of it. This psychological shift proved as important as the mechanical improvement itself. Confidence in equipment translated into aggressive tactics that maximized the Mustang's advantages in speed and dive performance. German pilots accustomed to fighting American escorts that had to moderate their performance to preserve mechanical reliability now faced opponents who could exploit every margin of aerodynamic superiority. The misaligned gear had removed a limiting factor that had constrained tactical doctrine, but the change also revealed how narrowly the solution had emerged. If Margaret Hastings had simply rejected the anomalous gear without additional testing, the discovery would never have occurred. If Dr. Miller had not proposed the resonance theory, the test program would never have been authorized. If Colonel Davidson had chosen regulatory compliance over operational effectiveness, the specification change would have been rejected. The successful innovation required a convergence of individual initiative, technical insight, institutional flexibility, and willingness to challenge fundamental assumptions about precision manufacturing. Remove any single element from that chain, and the Mustang would have continued suffering reduction gear failures that killed pilots and limited the aircraft's effectiveness at exactly the moment when long-range escort capability was becoming decisive in the strategic bombing campaign over Germany. The strategic implications rippled through Allied air doctrine throughout 1944. The Mustang's reliability at extreme performance enabled escort tactics that had been theoretically possible, but operationally risky with earlier aircraft. Fighter groups could now maintain close escort throughout the bomber stream's penetration into Germany, engage German interceptors aggressively without fear of mechanical failure during high-speed combat, and still retain sufficient fuel and mechanical integrity to return to bases in England. The cumulative effect was bomber loss rates that declined from catastrophic levels in late 1943 to sustainable attrition by mid-1944. This was not solely due to reduction gear reliability. Improved tactics, better training, and declining Luftwaffe capability all contributed. But the mechanical confidence that allowed aggressive escort tactics was fundamentally enabled by the misaligned gear that prevented failures at high-speed combat conditions. Major General William Kepner, commanding the 8th Fighter Command, recognized the transformation in a July 1944 operational assessment. Our fighters are no longer defending bombers by staying close and waiting to be attacked. They are hunting aggressively because they trust their aircraft to perform under the most extreme conditions. That confidence stems directly from mechanical reliability. We cannot quantify exactly how many bombers were saved, because P-51s could pursue German fighters through high-speed dives without concern for gear failure, but the impact is substantial. His assessment was supported by loss data. German fighter tactics in early 1944 had exploited American reluctance to pursue through extended high-speed engagements. Luftwaffe pilots would dive away from combat, knowing that mechanical concerns would limit how aggressively American escorts would pursue. By summer 1944, that tactical assumption no longer held. Mustang pilots pursued through dives that exceeded 500 miles per hour, confident that their reduction gears would survive the vibration and loads that such speeds generated. The tactical adaptation forced German fighters into prolonged engagements where American numerical superiority and pilot training advantages became decisive. The misaligned gear's contribution to this tactical evolution was invisible to intelligence analysts, but fundamental to its execution. Mechanics servicing P-51s in England knew that the rough-sounding gear mesh they heard during engine run-ups represented deliberate engineering rather than manufacturing defect. Pilots knew that their aircraft had survived the high-speed regime where earlier Mustangs had failed. The institutional knowledge filtered through the operational community, even though the specific engineering details remained classified to prevent German intelligence from understanding American manufacturing practices. The broader industrial implications emerged as other aircraft programs confronted similar vibration-related failures. The P-47 Thunderbolt, operating at similarly extreme performance levels, had experienced propeller reduction gear problems that paralleled the Mustang's early failures. Republic aviation engineers, learning of North American's solution, initiated their own testing of deliberately misaligned gear assemblies. The physics proved transferable. By autumn 1944, the P-47N variant incorporated reduction gears with controlled misalignment optimized for the Thunderbolt's specific vibration environment. The Navy's F-4U Corsair, already benefiting from the 75S alloy propeller improvements, received similar gear modifications that further enhanced reliability during carrier operations, where arrested landings created shock loads that excited problematic vibration modes. What had started as an anomalous discovery at a single manufacturing facility was becoming a design principle applied across American aviation. The recognition that deliberate imperfection could produce superior performance under dynamic loading challenged engineering orthodoxy in ways that extended far beyond aircraft reduction gears. Dr. Raymond Muller, whose vibration theory had enabled the breakthrough, published a classified technical paper in March 1945 titled "Detuning as Design Strategy: Controlled Imperfection for Dynamic Stability." The paper argued that precision manufacturing had been overemphasized at the expense of understanding operational environments. "We have pursued ever tighter tolerances under the assumption that perfection produces optimal performance," he wrote. This is true for static or steady-state conditions. It is often false for dynamic systems operating in complex vibration environments. Sometimes the optimal solution involves deliberately introducing controlled imperfection that destabilizes problematic resonances. His theoretical framework influenced post-war mechanical engineering curricula and contributed to the development of vibration isolation systems, dynamic balancing techniques, and structural damping approaches that would become standard practice in aerospace, automotive, and industrial machinery design. The misaligned gear that had saved the Mustang from structural failure became a case study in engineering education, illustrating the gap between theoretical optimization and operational reality. Yet Muller acknowledged the role of chance in the discovery. If Inspector Hastings had followed standard procedure and rejected that first misaligned gear, we would have continued pursuing solutions within the framework of precision manufacturing. We would likely have found an answer eventually: better materials, stronger gears, revised heat treatment. But we would not have discovered the fundamental insight that controlled detuning can solve problems that precision cannot address. The breakthrough came from someone noticing that a defective component behaved differently and asking why, rather than simply rejecting it. The human element in the discovery proved as important as the technical innovation itself. Margaret Hastings, the inspector whose curiosity prevented premature rejection of the anomalous gear, received recognition that was unusual for someone in her position. In an industry dominated by male engineers and executives, Hastings was one of relatively few women in technical roles with authority to make decisions that affected production. Her decision to authorize additional testing, rather than immediate rejection, represented initiative that went beyond standard quality control practice. She later described her reasoning in an oral history interview conducted in 1952. The gear was out of specification, no question about that. Standard procedure was rejection, but the test data showed it was behaving strangely, not badly. There's a difference. Something behaving badly is clearly defective. Something behaving strangely might be defective, or it might be revealing something we don't understand about how the system actually works. I thought it was worth investigating before scrapping a component that cost 300 hours of skilled labor to manufacture. Her distinction between bad and strange captured an epistemological insight that formal procedures struggled to codify. Quality control systems are designed to identify and reject deviation from specification. They are not designed to recognize when deviation might reveal inadequacy in the specification itself. That requires human judgment, curiosity, and willingness to question established standards. The recognition Hastings received was modest by later standards: a commendation from North American Aviation's president, a small war bond award, and acknowledgement in internal company communications. But within the wartime manufacturing culture, this represented significant validation for someone whose daily work normally remained invisible to management. Her example influenced how North American approached quality control in subsequent programs. Inspectors were encouraged to document anomalies rather than simply rejecting non-conforming components. A formal review process was established to evaluate whether deviations might represent opportunities for design improvement rather than manufacturing defects. The institutional change was subtle, but consequential. The same manufacturing facility that had nearly scrapped the misaligned gear in 1943 became, by 1945, an organization that systematically investigated anomalies as potential sources of innovation. The cultural shift reflected lessons learned through combat experience. Specifications were human artifacts that could be wrong, and the people closest to manufacturing and testing often possessed insights that formal engineering analysis might miss if institutional structures did not create space for those insights to surface. By early 1945, the P-51 Mustang had achieved air superiority over Germany, so complete that bomber losses to fighter attack had declined to less than 2% per mission. The reduction gear reliability that enabled aggressive escort tactics was one factor among many contributing to this dominance, but it was a necessary factor without which other advantages could not have been fully exploited. The aircraft's range, speed, and maneuverability mattered only if pilots could trust the mechanical systems to survive the extreme conditions that combat imposed. Lieutenant Colonel George Preddy, the leading Mustang ace in the European theater, with 83 confirmed victories, flew aircraft that routinely exceeded 500 miles per hour in combat dives. His tactics relied explicitly on the Mustang's ability to accelerate in descent faster than German fighters and maintain that speed advantage through extended pursuit. "The Mustang dives like a brick and accelerates like nothing else in the sky," he explained during a combat tactics briefing in December 1944. "You can run down anything the Luftwaffe has if you're willing to push it hard. The gear holds together. The airframe stays solid. You focus on shooting, not on whether your airplane is going to shake itself apart." Preddy's confidence was based on cumulative experience with aircraft that had proven their durability under conditions that exceeded original design assumptions. The misaligned reduction gear was invisible to him, just another component in a mechanical system that worked when subjected to extreme demands. Yet that invisible component was essential to the tactical approach that made him the war's most successful Mustang pilot. The statistical impact was measurable in aggregate even if individual contributions were difficult to isolate. P-51 units equipped with misaligned reduction gears maintained operational readiness rates averaging 85% compared to 73% for earlier units with standard gears. Over the final year of the European Air War, this reliability advantage translated into thousands of additional sorties flown, hundreds of additional German aircraft destroyed, and measurably reduced bomber losses across the strategic campaign. The reduction gear that was wrong by original specification had become essential to operational effectiveness at the strategic scale. The engineering innovation that had started as a curious anomaly discovered by a quality control inspector had evolved into a critical enabler of Allied air superiority, demonstrating how small technical improvements in critical components can produce strategic consequences, far exceeding their apparent significance when viewed in isolation. The final validation of the misaligned gear's effectiveness came not from statistical analysis or engineering theory, but from the ultimate test: survival rates of pilots whose lives depended on mechanical reliability under the most extreme conditions imaginable. Through 1944 and early 1945, as the air war over Germany intensified to levels of violence that strained both equipment and human endurance, P-51 pilots flew missions that regularly pushed their aircraft beyond every design parameter. Dives from 30,000 feet to 10,000 feet in pursuit of German jets, extended combat at 25,000 feet, where thin air and extreme cold challenged every mechanical system, high-speed, low-level strafing attacks against ground targets where even momentary engine failure meant certain death. In these conditions, the reduction gear that connected engine power to propeller thrust represented a single point of failure with no redundancy and no forgiveness. Captain Charles "Chuck" Yeager, who would later become the first human to exceed the speed of sound, flew combat missions in P-51s during this period. His assessment was characteristically direct. The airplane either works or it doesn't. When you're alone over Germany at 500 miles per hour with the engine screaming and the airframe shaking and every instrument reading redlined, you need to know that the critical components will hold together. The reduction gear is one of those components. It fails, you're done. It holds, you might make it home. The misaligned gear held. That's all that mattered. The survival statistics supported his observation. P-51 operational loss rates from all mechanical causes declined from 4.2% in late 1943 to 1.1% by early 1945. While multiple factors contributed to this improvement: better maintenance, improved pilot training, design refinements, the elimination of reduction gear failures removed one of the most feared and unpredictable mechanical failure modes. Pilots stopped worrying about whether their gear would survive high-speed combat and focused their cognitive resources on tactics, situational awareness, and survival. The psychological benefit of reliable equipment proved difficult to quantify but easy to observe. Squadron commanders reported that pilot stress levels, as measured by flight surgeon evaluations, declined notably after the transition to aircraft with misaligned gears. The elimination of a specific failure mode created downstream effects on mission performance that went beyond the mechanical improvement itself. Confidence enabled aggression. Reliability enabled risk-taking. The mechanical solution produced tactical advantages that cascaded through the entire operational system. The war ended before the full theoretical understanding of the misalignment's benefits could be completely developed. Post-war analysis by the National Advisory Committee for Aeronautics revealed complexities in the vibration dynamics that even Dr. Mueller's original theory had not fully captured. The misaligned gear mesh was creating what modern engineers would recognize as a nonlinear damping system. The micro-impacts between gear teeth introduced force displacement relationships that did not follow simple linear patterns. This nonlinearity prevented resonance buildup through mechanisms that were mathematically sophisticated but operationally simple. The system dissipated vibrational energy through controlled friction and impact forces that increased proportionally to vibration amplitude. High-amplitude vibrations encountered more damping than low-amplitude vibrations, creating a self-regulating system that prevented destructive resonance while allowing normal operational vibrations to pass through without excessive energy dissipation. The engineering elegance was remarkable precisely because it emerged without full theoretical understanding. The designers who implemented the misalignment knew it worked operationally, but did not initially comprehend all the physics that made it effective. This was not unusual in engineering practice. Many successful innovations precede complete theoretical understanding. What was unusual was the willingness to implement a solution that violated established manufacturing principles based on combat results rather than waiting for complete analytical validation. Dr. Sarah Chen, a NACE researcher who analyzed the reduction gear dynamics in 1946, concluded her technical report with an observation that transcended the specific technical details. The misaligned gear represents a class of engineering solutions that emerge from operational experience rather than theoretical prediction. We designed for precision based on principles that were correct for static systems. Combat operations revealed that dynamic systems often require different approaches. The lesson is not that precision is wrong, but that context determines what constitutes optimal design. In static or steady-state conditions, perfect alignment remains ideal. In dynamic environments with complex vibration inputs, controlled imperfection may produce superior performance. The challenge for engineering practice is creating institutional processes that can recognize when operational context demands solutions that theoretical analysis would not predict. Her report influenced post-war aerospace engineering practice, contributing to the development of design methodologies that explicitly considered dynamic operating environments rather than optimizing solely for static performance. The P51 reduction gear became a case study in engineering schools, illustrating the principle that optimal design depends critically on operational context and that solutions emerging from field experience can reveal inadequacies in specifications developed from theoretical analysis alone. The P51 Mustang's final combat record speaks with numbers that transcend engineering analysis. 4,150 enemy aircraft destroyed in air combat, more than any other Allied fighter in the European theater. The aircraft flew 213 to 873 sorties, escorted heavy bombers through 469 missions deep into Germany, and achieved this while maintaining mechanical reliability rates that exceeded every previous American fighter program. The reduction gear that should have been rejected as defective instead became essential to this success. The operational availability enabled by reliable reduction gears translated into strategic capability at scales that individual component engineering could not have predicted. The misalignment that violated manufacturing specifications enabled aircraft availability, that enabled mission execution, that enabled bomber protection, that enabled strategic bombardment that contributed to Allied victory. The causal chain was long and complex, but each link was necessary. Remove the reduction gear reliability, and the chain breaks. Mustangs would have been forced to moderate their tactics to preserve mechanical integrity, reducing their effectiveness precisely when maximum performance was essential. The German Air Force would have retained capabilities that history records were destroyed. Bomber losses would have remained at unsustainable levels, potentially forcing revision of strategic bombing doctrine. These counterfactual scenarios are speculative, but they illustrate the principle that small technical innovations in critical components can produce strategic consequences far exceeding their apparent significance. A 4,000th of an inch misalignment in a gear mesh becomes a factor in air superiority over Europe. The engineering achievement was remarkable not because it required advanced theoretical knowledge or sophisticated manufacturing capability, but because it required willingness to question fundamental assumptions about precision manufacturing. The institutional challenge was not building the misaligned gear, that was technically trivial, but recognizing that deliberate imperfection could be superior to specification compliance. The breakthrough came from Margaret Hastings asking why rather than simply rejecting, from Dr. Muller proposing a theory that challenged conventional wisdom, from Colonel Davidson choosing operational effectiveness over regulatory comfort, and from thousands of pilots whose survival depended on whether engineers could solve a problem that standard approaches had failed to address. The misaligned gear saved the Mustang from structural failure at 500 miles per hour, but it also saved lives, enabled missions, and demonstrated that excellence sometimes emerges from questioning whether the pursuit of perfection might itself be the obstacle preventing optimal solutions. The P-51 Mustang remained in military service until 1984, when the final examples were retired from air forces of smaller nations that had operated the type for decades after American forces moved to jet fighters. Some of these aircraft still had their original reduction gears, components manufactured in 1944, with deliberate 4,000th inch misalignment, still functioning after 40 years of operation. The longevity validated what combat had proven. The wrong gear had been exactly right. Margaret Hastings continued working in aerospace quality control throughout her career, eventually becoming one of the first women to hold senior management positions at North American Aviation. In a 1978 interview, shortly before her retirement, she reflected on the reduction gear discovery. People ask if I knew how important it would be when I authorized those additional tests instead of rejecting the gear. I didn't. I just thought it was interesting that something out of specification was behaving strangely rather than badly. I wanted to understand why before discarding it. That curiosity happened to matter because we were at a moment when conventional approaches weren't solving the problem. Sometimes the most important contribution you can make is asking questions rather than following procedures. Her observation captured a truth that extends beyond engineering into every domain where innovation confronts established practice. Progress often requires someone to notice that an anomaly might be revealing rather than defective, to ask why rather than simply reject, and to create space for unconventional solutions to prove themselves through performance rather than conformity to specification. The reduction gear's misalignment became a principle that influenced engineering practice for generations. Modern vibration control systems, from helicopter rotors to turbine blades to precision manufacturing equipment, incorporate controlled detuning strategies derived from lessons learned when a defective P-51 component proved superior to specification-compliant alternatives. The technical lineage is direct and documented. What remains harder to quantify but equally important is the institutional lesson. Sometimes specifications are wrong, and the people closest to manufacturing and operation can recognize this before theoretical analysis reveals it. Creating organizations that can act on those insights requires cultural values that prize curiosity over compliance, that validate performance over procedure, and that recognize excellence sometimes emerges from unexpected places. The misaligned gear taught that lesson in steel and combat results. The lesson endures wherever human organizations confront the gap between how things should work according to theory and how they actually work in reality that refuses to conform to our models of it.